So, in the last lecture, we have discussed several tests for judging the absolute convergence of the series of real numbers, and those sets mainly we have discussed the nth root test, comparison test, ratio test, integral tests. Now, even we see that these tests are good enough to judge the series to be convergent, absolutely convergent or not, but still there is a case of failure. When the limit of x n to the power 1 by n, limit of x mod x n to the power 1 by n as n tends to infinity, if this limit comes out to be 1, or limit and similarly and limit of this mod x n plus 1 over x n ratio test as n tends to 1 comes out to be 1, then both both nth root test and ratio test fails. Root test and ratio test fails. We are unable to decide whether the given series is absolutely convergent or divergent, or it may be convergent, may be divergent depending on this. So, a further test which will help in this direction is given by Raabe, which is known as the Raabe test, and that can be applied only when we see that this test fails. We can also, but initially when we start with that, we always consider step by step, go step by step, and then if required, then we come for the higher order, higher level tests. So, Raabe test says that is, let x, which is x n, be a sequence of non-zero real number, be a sequence of non-zero real numbers. Now, first part, if there exist numbers a which is greater than 1 and k which belongs to n, the set of natural number, k is a positive integer, k get such that mod of x n plus 1 divided by x n under mod is less than equal to 1 minus a by n for all n greater than equal to k. Then the Raabe test says the series sigma x n is 1 to infinity converges is absolutely convergent. Now, on the other hand, if there exist real number, numbers a which are less than or equal to 1 and k is a positive integer such that mod of x n plus 1 divided by x n under mod, if it is greater than equal to 1 minus a by n for all n greater than equal to k, then the series sigma x n 1 to infinity is not absolutely convergent. It means it will be a diverging series, absolutely convergent. The proof of this follows as it is. Suppose let us give this number, suppose this is inequality 1, this is 2. Suppose 1 holds. Then we have to show the series is absolutely convergent. So, 1 holds means mod of x n plus 1 by x n is less than equal to 1 minus a by n. There exists a number a greater than 1 such that this is true for all n greater than equal to k. So, let us replace n by k, small k suppose. Then what we get is here that k into replace n by small k. It's nothing, no problem, it's n, and then we multiply this. So, k into mod x k plus 1 minus less than equal to k minus 1 into mod x k minus a minus 1 mod x k. This is true for all k greater than equal to capital K. What I did is I just used this in place of n, let us say small k. So, when you multiply by this k, you are getting a k times mod x k plus 1 is less than equal to 1 minus a into mod x n. This can be manipulated like this. It can be written as k minus 1 mod x k minus this, because mod x k gets cancelled from here, and basically you are getting this k minus a into mod x k. Okay. So, this way we are doing. Now, again reorganize it. So, this implies that k minus 1 into mod x k minus k times of mod x k plus 1. This term is greater than equal to a minus 1 into mod x k, and this is true for all k greater than equal to capital K. Now, a is strictly greater than 1 in the case 1, first case. So, a is greater, so this is a positive quantity. This is also a positive quantity because we are choosing x n as a sequence of the non-zero real number. So, mod of x k will be positive quantity. So, what it shows? This shows that k times of mod x k plus 1 basically is what is a decreasing sequence. So, what we get is, so this implies that the sequence k into mod x k plus 1 x k plus 1, this sequence is a decreasing sequence of real numbers for k greater than equal to capital K. Okay. Now, if I add this one, let it be this quantity k minus 1, let it be 3, this third. Okay. Now, if we add this from use 3 and add for small k is capital K plus 1 up to say n. So, when you add, this will automatically telescopically few term will get cancelled, and finally, we get capital K minus 1 into mod of x capital K minus n mod of x n plus 1 is greater than equal to a minus 1 into mod of x capital K plus mod of x n. Okay. Now, since a is greater than 1, so a minus 1 is non-zero. So, a minus 1 is different from 0. We can divide by this. So, this implies that mod of x capital K plus up to mod x n, then plus n by mod x n plus 1, n times mod x n plus 1 divided by a minus 1 divided by this a minus 1, this a minus 1, this term you are taking here, okay, and divide by a minus 1 is less than equal to capital K minus 1 divided by a minus 1 mod of x k. Okay. Okay. Now, k is any numbers, is it not? So, k minus is a fixed number, k is also fixed. So, this is basically a finite quantity, this is finite, okay, bounded. Now, here if I look this one, n is greater than mod a minus 1, because once a is fixed, then n can be taken so large, so that n over a minus 1 is greater than 1. So, basically this entire thing is greater than the series sigma mod x I is capital K to n plus 1 is greater than this. So, what does show? That this series, when n is sufficiently large, this is bounded series. So, this implies that the series sigma mod x n, this series is a bounded partial sum of this series, partial sum of the series this is bounded. Okay. So, partial sum of this series is bounded 1 to infinity, and the series and the terms of this series k into x minus is a decreasing sequence of real numbers, is it not? So, this is a bounded sequence and monotonically decreasing sequence of real number, because once it is decreasing, mod x k minus 1 will also be k times. Okay. So, this is a bounded sequence, hence every bounded sequence is a convergent one, monotonic. Okay. So, this shows that the sequence, this implies the series x n 1 to infinity converges absolutely. Absolutely. So, this is the proof for this part 1, this is part A. Proof for part B. Now, in this case, it's we given that this relation given that there exist real numbers a less than or equal to 1 and k a positive integer such that mod of x n plus 1 y x n is greater than equal to 1 minus a by n for all n greater than equal to k. So, what this show? This shows that if we multiply this n into mod x n plus 1, this is greater than equal to n minus a into mod x n minus a into mod x n. But what is? But a is less than equal to 1. So, minus a is greater than equal to minus 1. So, it is greater than equal to n minus 1 mod of x n, as a is less than equal to 1. So, n of mod x n is greater than, this implies the sequence n into mod x n plus 1. This sequence is an increasing sequence. Increasing sequence of real numbers for all n greater than equal to capital K, for all n greater than equal to capital K. So, once it is increasing, so if we take any c, then n can be obtained, so that is greater than equal to c. So, and there will exist a number c. So, there exists a number c greater than 0 such that this mod x n plus 1 is greater than c by n. Okay. And this is true for all n greater than equal to capital K. Therefore, the sigma of this x I is n plus 1 to say infinity is greater than c times sigma of 1 by I is n plus n to infinity. Now, this is a harmonic series. This is a harmonic series. So, what we do is that if I take I equal to 1 to infinity, that is sigma I is equal to 1 to infinity mod of x I is greater than equal to, say, same terms we are adding here. So, some c replaced by c dash is greater than equal to sigma 1 to infinity 1 by I. Is it not? Some few terms we are adding here. So, that can be written as a some C dash sign or maybe plus something, but this is a harmonic series. Harmonic series. So, once it is harmonic, it means it will be a diverging one. So, diverges. So, once it is diverges, this series will be diverging one. So, this implies that series sigma mod x n is 1 to infinity is not absolutely convergent, is not convergent. Therefore, original series will not converge absolutely. So, that is the reason for this. Okay. Now, the equivalent is a corollary of this, because it is difficult to get this ratio. So, in terms of the limit, we can easily get this test which is applicable, and so as a corollary we can say, let x which is x n be a non-zero sequence in R, set of real number, and let A is the limit of this, limit of n 1 minus mod x n plus 1 by x n mod of this as n tends to infinity is suppose A, whenever this limit exists. Okay. So, this then this series sigma x n 1 to infinity, this is absolutely convergent, when A is greater than 1 and is not absolutely convergent when A is strictly less than 1. For A equal to 1, again test fails, we are unable to get. So, we have to apply some other tricks for that. Okay. A is less than 1. The proof runs as usual. Suppose the limit in this, let it be this 3. Suppose third exists, limit exists in 3. So, it means the limit of this is A, where A is strictly greater than 1. So, we can identify. So, there exists. So, if A 1 is a number, A 1 is such which lies between A 1 is less than A 1 less than A. For this A 1, there exists some k, a positive integer k, such that A 1 is less than n times of 1 minus mod x n plus 1 by x n for all n greater than capital K. This is because this limit is A, okay, and A is strictly greater than 1. So, if I choose a number in between 1 and A, it means there will be a sequence of the term of this series which will exceed by A 1, then only the limit will go to A. Okay. There are the sequence, because limiting is going to A. This is 1, here is A, the limit is going tending to this. So, what I am doing is I am choosing one A 1 here. Okay. So, an n can be obtained, a k can be obtained such that when you take all n greater than k, all the terms of the sequence will fall here, that is they are greater than A 1. So, if it is so, then what happens to that? Therefore, this series when this converges, so we get from here that therefore, this implies what? n plus x n plus 1 over x n. This will be, when you transfer it, what you are getting is less than 1 minus a 1 by n. Okay. But a 1 is what? And this is true for all n greater than k. But a 1 is strictly greater than 1. So, by Raabe's test, since a 1 is strictly greater than 1, so by Raabe's test, the series sigma x n 1 to infinity converges absolutely. Similarly, for the other, similarly, if a is less than 1, the result follows. In a similar way, you can prove that this result is true. Okay. Now, we have seen the corollary and the result. Now, this corollary is weaker, basically the result is very strong, that is, this ratio, this type of thing is stronger than this one, which can be seen easily by the following example. Suppose I take this problem, let us consider the series sigma n over n square plus 1. Test for the convergence, absolute convergence, all the terms are positive, test for the convergence of this series. Now, if we apply the results here, suppose I take here the x n is n over n square plus 1. So, x n plus 1 becomes n plus 1 whole square plus 1. So, when you take the x n plus 1 y x n mod of this, then what happens to the x n plus 1 over here? This comes out to be what? N plus 1 by n, this term, and then n square plus 1, n plus 1 whole square plus 1, and then limit of this as n tends to infinity, limit of this as n tends to infinity. Now, limit of this is 1, again when you divide by n square, the limit will come out to be what? This is 1, and then this limit x n plus 1 by x n plus 1 by x n over n plus 1, it is 1 or not. Let us see, n square plus 1, so 1, then 1 and plus 1 2. So, why it is n plus 1, calculation limit of this is x n is n over n plus 1. So, if you take this n plus 1, n plus 1, n plus 1. So, divide by n plus 1 square, ठीक है, divide by n plus 1. So, we get from here is n plus 1 square. So, what we are getting is 1, divide by this n plus 1 square, this is, sorry, that is why it is a mistake, this is n plus 1, not n. Okay. So, divide by n plus 1 square here. So, this limit is 1, this limit is 1, product will be 1. So, the ratio test fails. Now, if I take the Raabe's test n into corollaries of the Raabe minus x n plus 1 over x n, this thing, and then take the limit of this as n tends to infinity, then again you will see this limit comes out to be 1. Okay. We can just solve it and get this, we get the limit to be 1. So, again fails. Okay. We are unable to do that, but this is by corollary. But if we look the x n plus 1 by x n, what you are getting? X n plus 1 by x n, this is nothing but what? Is greater than or equal to n minus 1 by n, is greater than equal to n minus 1 by n. If you just see the ratio of this and find out the term, you will get this is greater than equal to, that is 1 minus 1 by n. Okay. And this is positive 1. So, this diverges. So, by Raabe's test, the series sigma x n does not converge absolutely. So, this shows that though the Raabe test is difficult to find out these type of ratios and get the decision, but it is much stronger than the corollaries of this Raabe test. Okay. So, but practical the corollary is much more easy to apply rather than to this. Okay. So, that is what. So, this is all about this convergence or absolute convergence of the series.